So next I would like to show an explicit calculation how you can calculate a differential cross-section for a specific potential. And the specific potential I would like to pick is again the Kepler type. So we are looking at potentials of the form u as a function of distance equals minus some constant alpha over the distance r. Now here we don't specify whether the alpha, this constant alpha, is positive or negative. If alpha is positive, as in the gravitational case, the gravitational force, then the potential is attractive. If, on the other hand, the alpha is negative, then the potential is repulsive, and this is the case, for example, if you have two electric charges of the same sign that you scatter off each other. So you have the Coulomb force between two electric charges, and the potential is also of the Kepler type, but the alpha is negative if the charges have the same sign. And that is the situation that you have in the classic Rutherford scattering experiment, where you have positive nuclei, positively charged nuclei that are scattered off each other. Now, we already discussed in the context of the Kepler problem that for bounded motion we have an ellipse, we have the shape of an ellipse. For unbounded motion, and that's what we have in a scattering experiment, the geometric shape of the orbit is a hyperbola. Now, if you think here of this black dot as the center of the potential, then in the attractive case, the hyperbola will approximately look like that. You have asymptotically free motion. So think of this black dot as the sun, and the other particle, sort of a small comet, comes from outside the solar system, enters the solar system. So far away it moves uniformly, then it feels the attractive force of the sun, and then it turns around and leaves the solar system again. The shape of the orbit will be that of a hyperbola, as I said, and the orbit will approximately look like that. At each point along this orbit, we characterize the position of the particle, the projectile, the comet in this case is the projectile, with polar coordinates. So we have the distance from the center of the potential, little r, and we have an angle phi. Note that this phi is not identical to the phi that we used earlier in this experimental setup. There we used phi to denote the angle around the beam axis. Here it's a different phi. It's the phi that we used in the solution of the Kepler problem in polar coordinates. Now, in the repulsive case, the situation is slightly different. Again, let me denote with the black dot the center of the Kepler potential. Again, asymptotically, the motion of the target is free. It's uniform asymptotically. The shape of the orbit is again a hyperbola, but this time it looks slightly different. We have the projectile coming in, feeling the repulsive force of the potential, turning around and going back asymptotically free. So you see the difference between the repulsive and the attractive case. Again, at each moment, the position of the projectile in the center of mass frame is characterized by these two coordinates, r and phi. We can extend this straight line that corresponds to the asymptotic motion of the incoming projectile. If we didn't have the scattering of the center of the potential, then the projectile would simply continue on this straight line. It would continue on this dashed straight line. But since it feels the repulsive force of the central potential, it's deflected off this straight line. And the scattering angle that we had introduced earlier is this angle here. This purple angle, that's the scattering angle theta. Initially, far away, when the projectile comes in, and still far away from the center of the potential, the angular coordinate of the projectile will be this one here. This, and let me call that phi infinity minus. Okay? So this is the asymptotic angular coordinate of the incoming particle. After the scattering, when it moves away, and then again far away from the scattering potential, the asymptotic angular coordinate is this one here. And this I call phi infinity plus. Right? So the green angles are the asymptotic angles, the asymptotic angular coordinates of the projectile at time minus infinity, so still far away from the potential, and at time plus infinity, so after the scattering process, and then far away from the center of the potential. You recognize from this drawing that there's a relationship between the scattering angle theta and these two asymptotic angles phi plus and phi minus. And the relationship is that the scattering angle theta is pi minus the difference of phi plus and phi minus. Yeah, so you look at the difference between the two green angles, the two asymptotic angles. That is the angle between the sort of the straight line that characterizes the incoming, it's asymptotic incoming trajectory, and the other straight line that characterizes the asymptotic motion of the outgoing particle. So that's the angle between these two gray lines. That is the difference between the asymptotic angles. And then add to that the scattering angle theta, and they add up to pi. Yeah? So you solve that for theta, and you get this relationship here. I would like to focus from now on the repulsive case. So we take this scenario on the right, that we have a repulsive Kepler potential. So on the previous page, we expressed the scattering angle in terms of the asymptotic angles, phi plus and phi minus. So what we should do next is we should try to calculate, to determine the asymptotic angles. And to do so, I would like to recall from our discussion of the Kepler problem, I would like to recall the equation that we had found. We had found this equation here, that's inside the box. And I had mentioned when we discussed that this formula, when we derived that formula, that this formula is valid universally. It doesn't, for the Kepler potential, it's not restricted to the bounded motion that we had discussed earlier, but it's valid both for bounded and unbounded motion. So it's also the relevant equation for the scattering case that we are looking at here. Now in this equation feature two parameters, kappa and epsilon, that we had introduced. And I would also like to recall the definition of these two parameters. So kappa and epsilon are defined here. And as I had said, we would like to focus on we'd like to pick here the repulsive case. In that case, alpha is smaller, is negative, and therefore also kappa is negative. Yeah? So this is for the repulsive case. So one thing we can do is in this equation inside the box, the kappa is negative, we can replace it by the absolute value of kappa, which is then a positive quantity, and to compensate for that, we introduce minus signs on the right-hand side. In the definition of epsilon, there's the ratio kappa over alpha. Kappa is negative, but alpha is also negative, so the signs cancel out. And in the scattering regime, the energy E is positive, is larger than 0, and therefore the epsilon is the square root of a quantity which is larger than 1, and hence the epsilon is larger than 1. So this is for the scattering case. Okay, and finally, this is just a matter of notation. At the time we used the coordinate rho, but here I'm discussing this in terms of the coordinate r. I changed letter, so I hope you forgive me this slight change in notation, and therefore here we have, instead of rho, we have r. So we've adapted we've collected here all the input and all the formulas that we need and adapted them to the current notation. How can we find the asymptotic angles? Well, the asymptotic angles correspond to infinite distance of the projectile from the center of the potential. So when r, the distance of the particle to the center of the potential, goes to infinity, right? So we should look at the case r going to infinity. Then, of course, on the left-hand side of our equation in the box, this ratio kappa over r, kappa is just a constant, this goes to 0. And therefore, the cosine of phi infinity, so this is an asymptotic angle, the cosine of an asymptotic angle must equal minus 1 over epsilon. Right, so we set the left-hand side equal to 0, we solve for the cosine of phi, and then we find this relationship here, this condition for the cosine of the asymptotic angle. We can slightly rephrase it. We can say well, if the cosine of phi is minus 1 over epsilon, we can shift by pi, and this must be equal to plus 1 over epsilon. And this we can solve for phi. And this must be pi plus the arc cosine of 1 over epsilon. Well, of course, when we invert the cosine, then we always have two possible solutions. We have not only pi plus arc cosine, but also pi minus arc cosine. That's also a possible solution of the equation. So in fact we have pi plus or minus, and hence we find two possible asymptotic angles, and these correspond to the incoming and the outgoing asymptotic angle. So we have here our plus or minus. Now remember the formula that we had on the previous page for the scattering angle. That was pi minus the difference of the two asymptotic angles. We can insert our result for the two asymptotic angles and find that this is pi minus 2 times the arc cosine of 1 over epsilon. Or in other words, we can say theta over 2. This is pi over 2. Well, this is extremely simple, like that. And this finally we can take on both sides we can take the sine and then use just the trigonometric relation between sine and cosine. We find that the sine of theta over 2, that's the sine of the right hand side, and this is equal to 1 over epsilon. And so for the Kepler case, we find a very simple formula for the scattering angle. Very simple condition for the scattering angle. So what we've achieved up to this point is that we have a formula for the scattering angle in terms of this parameter epsilon. That's not yet what we need, because in order to calculate the differential cross-section, we need theta as a function of impact parameter. So what we have yet to do is to express the epsilon in terms of impact parameter, and if we can do that, then we have theta as a function of impact parameter, and then we can calculate the differential cross-section. Well, doing that leads then to the Rutherford formula. Remember the definition of epsilon that was defined as the square root of 1 plus 2e, I think was defined in terms of kappa, but kappa in turn, and then we insert the definition of kappa, and then we find that epsilon has this form as the square root of 1 plus 2 times energy of the incoming particle times orbital angular momentum squared of the incoming particle divided by reduced mass alpha squared. That's the combination of the two formulas that we had on the previous page. But then early on, when we introduced the setup for the scattering experiment, we had also found a relationship between angular momentum and impact parameter. Let me just flip back to that page. Below, you see it's the last line on the left-hand side. You see a formula for the angular momentum, L. And on the last line, L is expressed in terms of impact parameter. They are simply proportional. We use this result, this relationship, and immediately we have then epsilon as a function of impact parameter. So this is equal to 1 plus, and then if I consider correctly the constant of proportionality, it's 2 times E times impact parameter divided by alpha, all of this squared and under a square root. And this, remember, we had just shown on the previous page, 1 over epsilon, that's the sine of theta over 2. So epsilon itself is 1 over sine of 1/2 the scattering angle. So we take this last equality here on this line, and we solve for the impact parameter. Now I'm going to skip the details. It's just straightforward algebra and some trigonometric relation that you can easily look up. And you find impact parameter as a function of scattering angle, S as a function of theta, is equal to the absolute value of alpha divided by 2 times energy times the cotan of 1/2 the scattering angle. We can also express that in terms of sine and cosine. So this is absolute value of alpha over 2e times the cosine of 1/2 the scattering angle over the sine of 1/2 the scattering angle. So this is the relationship between impact parameter and scattering angle that we need for the differential cross-section. What features in the formula for the differential cross-section is also the derivative of that function. So we should determine that the derivative of ds over d theta, absolute value, this is absolute value of alpha divided by 4e, and then the derivative of the cotan is 1 over sine squared. So we have 1 over sine squared 1/2 the scattering angle. So this is something that we will need. And then finally, a simple trigonometric relation that is helpful. We can express the sine of theta that features in the general formula for the differential cross-section. There's a sine of theta. We can write it as 2 times sine of theta over 2 times cosine of theta over 2. That's a simple trigonometric relation. And then we are ready to calculate the differential cross-section. Remember the general formula for the differential cross-section. That was scattering impact parameter as a function of scattering angle divided by the sine of theta times the absolute value of the derivative ds over d theta, and then we use our various results. We use the formula for s of theta. This is the absolute value of alpha divided by 2e times the cosine of 1/2 the scattering angle over the sine of 1/2 the scattering angle. This is our s of theta. Then for 1 over sine theta, we use this trigonometric formula. So we write 1 over 2 times sine of theta over 2 cosine theta over 2. Yeah, so this here, This is 1 over sine theta. And finally, we need the absolute value of the derivative. And that is absolute value of alpha over 4e times 1 over sine squared theta over 2. So this here, that is ds over d theta. Now there's the cosines cancel, and the remaining terms, they can be summarized in this formula for the differential cross section, d sigma over d omega as a function of theta. We have the factor alpha twice, so we get an alpha squared, and we have the factor e twice in the denominator, so we get an e squared in the denominator, and then we have numerical factors 2 times 2 times 4, so that's 4 squared, so we have a 4 in the denominator. And then what's remaining is 1 over sine of theta over 2, so half the scattering angle. And that factor we have a total of 4 times, so we have this to the power 4. And this is the famous Rutherford formula for the differential cross-section in the Kepler potential. Just as a historical remark, you may remember that the Rutherford scattering experiment was performed to confirm the atomic structure of matter. That was a way of showing that indeed matter was made of atoms. The experiment did not, however, give any evidence that classical mechanics was wrong. So it does not give any hint that there should be something like quantum mechanics, because it turns out, and that's a funny coincidence, that when you derive the scattering cross-section, the differential cross-section in quantum mechanics for the Kepler potential, you get exactly the same formula. So there's no difference between the classical and the quantum mechanical formula for the differential cross-section. So from that experiment alone, you cannot deduce yet that there is something wrong with classical mechanics.